Hello, everyone. This is Rishabh Nagtra, founder and admin of the Secrets of the Universe. We welcome you to the fourth episode of the Scientific Saturday Lecture. Our guest for today is an internationally renowned theoretical particle physicist, Professor John Ellis. He pioneered the particle studies of the Higgs boson in 1975. The discovery of the gluon by experimental teams at DESY in 1979 was based on an idea he published in a paper in 1976 and suggested to them. In 1977, he used a grand unified theory to predict the mass of the bottom quark, and in 1989, he used precision electroweak data to predict the mass of the top quark. He has also pioneered studies of supersymmetry, dark matter, string models, and quantum gravity. Much of his research work has concerned the prospects for particle accelerators, such as CERN's past, present, and future colliders. He is known for his efforts to develop a global collaboration in CERN's scientific activities. His many public lectures in the UK and elsewhere have opened pathways of scientific discourse all around the world.
Hi, I'm Vishaka, founder of Gurukul Academy. And before we invite Professor John Ellis for this lecture, I would like to remind everyone that we'll be taking questions after the presentation. So you all post your queries in the comment section and we'll be taking it once the lecture is over. We welcome you, sir. And we are very fortunate and privileged to have you with us today. And without further ado, we request Professor to begin the session. Thank you so much, sir.
Okay, well, thank you very much for the introduction. So it's a pleasure for me to join you, if only at a distance. So my title today is Answering the Big Questions. And I'm going to range over topics from the very small, in particular particle physics, and particularly the Higgs boson, to astrophysics, cosmology, with an emphasis on the dark side of the universe, in particular dark matter. So in this picture here, you see Peter Higgs, who is famous for having proposed the Higgs boson back in 1964. And as we'll see in this talk, a lot of present particle physics and the future connection with cosmology is connected with him and his work. So what do I mean by the big questions? So this is a copy of a famous painting by Paul Gauguin. And these are people on a South Sea island who are asking themselves what I consider to be very big questions. What are we? Where do we come from? Where are we going? So, some people approach these questions from a philosophical or a metaphysical point of view. I'm a scientist. I approach it from a scientific point of view. And I'm going to be discussing how physics, in particular particle physics, can address Gauguin's big questions. Now, if I was going to sort of boil it down to one single question, the aim of particle physics, I would say, is to understand what the matter in the universe is made of. So what is matter made of? Well, this you can regard as being Gauguin's big first question. What are we? And as we'll see in a moment, a key aspect of that question is why do things weigh? Why do particles weigh? Why does the electron have a mass? If it didn't have a mass, it would fly away from atoms at the speed of light, and there wouldn't be any atoms, there wouldn't be any matter, there wouldn't be any you, there wouldn't be any me. Of course, something else is we need to understand where the particles of matter in the universe came from in the first place. Presumably sometime back early in the history of the universe, there was some process which gave rise to the appearance of matter. What was it? So I already mentioned dark matter. Astronomers tell us that there is more invisible dark matter that does not emit light through the universe, more dark matter than there is regular matter. What is it made of? And of course, there's a whole bunch of other questions related to Gauguin's other big questions. How does the universe evolve? Why is the universe so big and old? And course, Gauguin's last question: what is the future of the universe? So our job as particle physicists is to answer these questions. I should say that when I started off as a PhD student, I had a copy of Gauguin's painting on the wall of my office just to remind me why I came in to work each day. And that's still why I come in to work. Anyway, as I said, our job as physicists is to ask and hopefully answer these questions. And I've outlined in green here the fact that we need physics beyond what we know to answer many of these questions. And those are what we're going to be studying in future experiments at the CERN Large Hadron Collider. So what do we know about the universe? So we know it's expanding. It's been expanding for something like 13.8 billion years. And now it's grown to a size of about 10 to the 28 centimeters for the visible universe. It may extend much further than that, but that's what we can see. Okay, so now we can ask Gauguin's questions again. So what is the stuff in the universe, those stars, those galaxies, what are they made of? Where do we come from becomes what happened at the beginning of the expansion of the universe, what we call the Big Bang. And where are we going? What is going to happen in the future of the universe? And as I promised, I'll touch on all three of these big questions. So if we go back and look towards the beginning of the universe, we can already pick out various different steps, things that happened in the behavior of matter in the very early universe. So nowadays, of course, we're made of atoms. But back when the universe was less than 300,000 years old, there were no atoms. The temperature of the universe was so high that there was just a plasma of elementary particles and nuclei. In fact, if we go back when the universe was less than 3 minutes old, there would not have been any nuclei because the temperature, the pressure was so high that those nuclei would just be dissociated. And in fact, if we go back beyond 1 microsecond, before 1 microsecond after the Big Bang, the constituents of nuclei, the protons and neutrons, wouldn't have existed either. There would have been a plasma of their constituent quarks and gluons. And if we go back to a picosecond after the Big Bang, a millionth of a second after the Big Bang, that's when we believe that particles acquired their masses thanks to Mr. Higgs, and we'll be coming back to later on. Okay, so those are some important steps in the history of the universe. Dark matter, we think, may have come out of the primordial plasma sometime between a picosecond and a microsecond after the Big Bang. And matter itself, the stuff that you and I are made of, may have appeared perhaps a picosecond after the Big Bang. And I'll come back to that later in the talk. But perhaps I'm getting ahead of myself a little bit. So we are made of molecules. Molecules contain atoms. Atoms contain nuclei surrounded by clouds of electrons. Those nuclei contain objects called protons and neutrons that were identified in the first half of the last century. But then in the second half of the last century, physicists realized that those protons and neutrons were made of more fundamental constituents called quarks. Now, as far as we can tell at the moment, electrons and related particles, quarks, those are the fundamental building blocks of matter. But one of the things that we try to do in our experiments, in particular at CERN's Large Hadron Collider, is to look inside the proton, inside the quarks, inside the electrons to see what is the fundamental structure, the fundamental interactions in the universe. So the accelerators that we build are certainly super microscopes. And by looking at what's going on at very small distances, very high energies, we're also able to study what happened in the very early history of the Big Bang, because early in the history of the Big Bang, particles had very high temperature, they had very high energies, and their interactions are what we recreate with our experiments at the Large Hadron Collider. So over on the right here, we have some astronomical observations. So here you see some stars, you see some galaxies. As I already mentioned, what the astronomers tell us is that in addition to this visible matter in the universe, there is also dark matter. Where did the dark matter come from? Well, as I mentioned on the previous slide, it may well have come produced by collisions in the very early universe that maybe we can reproduce with the Large Hadron Collider at CERN. Okay, so that's a sort of introduction to the structure of the matter in the universe. In fact, much of this structure was revealed by studying cosmic rays. So cosmic rays were discovered a bit over a century ago. This guy, Victor Hess, went up under a balloon and he found that there were very energetic things hitting the upper atmosphere, nuclei, particles. And when they hit the upper atmosphere, their energy was converted into showers containing many, many different types of particles. And in fact, many of the fundamental building blocks were discovered first in cosmic rays. For example, antimatter was discovered in the cosmic rays. The muon, a heavier partner of the electron, was also discovered there. But it's very difficult to study the properties of these particles in detail just by looking at cosmic rays. And that's why physicists, around the middle of the last century, started building particle accelerators so that they could do experiments in the laboratory and they could manipulate the particles making the collisions and study their interactions in great detail. So the basic principle is that we collide particles. So here, for example, you see a little drawing of a collision between two protons, like what we collide in the Large Hadron Collider at CERN. And when they collide, they produce showers of other particles coming out of the collision, which are then detected by particle experiments using various electronic devices. And these accelerators, these colliders, these experiments, you can regard as I mentioned earlier on, being like super microscopes. And these collisions reproduce the conditions at the beginning of the Big Bang and hopefully enable us to reconstruct what happened near the beginning of the universe. So what have these experiments revealed so far? So they have verified something that we call the standard model of particle physics. So this is a theory that was proposed in the 1960s by Abdus Salam, originally from Pakistan, and two American theorists, Shelley Glashow and Steve Weinberg, who unfortunately passed away just recently. So they proposed their theory in the second half of the 1960s, building upon the ideas proposed earlier by Peter Higgs and others. And then in the early 1970s, experiments at CERN verified the first key prediction of the standard model. And subsequently, experiments at CERN and elsewhere verified many more predictions with extremely high precision. So to call it a model is a bit of an understatement. It's actually a theory which we can calculate very reliably and gives us beautiful agreement with the experiment. So for example, if I look at this middle picture here, you can perhaps see a little red dot there. That little red dot represents an experimental measurement, and the green line is the theoretical prediction. And they agree perfectly. It's all the more impressive when you realize that little red dot has been expanded by a factor of 10 so that you can see it. Okay, so here in a little bit more detail, I describe the content of this standard model of matter. So in the top half of the slide, we have the various different constituent particles of matter. So over here we have the electron. There's a heavier sibling of the electron called the muon, which, as I mentioned, was discovered in cosmic rays, and another one, even heavier, discovered in particle accelerators. I mentioned that the fundamental constituents of nuclei are quarks, and we now know that there are 6 different types of quark. Now, between these particles of matter, we have various fundamental interactions. Clearly, there's gravity, which everybody knows about. There's electromagnetism, which was unified by Maxwell about 150 years ago. And then, at the level of fundamental particles, we know about the strong nuclear force that holds nuclei together, and the weak nuclear force responsible for forms of radioactive decay. Now, in addition to the particles on this slide, there has to be something else, because there's no explanation on this slide for where the particle masses come from. And this is important. If the electron didn't have a mass, as I already mentioned, there wouldn't be any atoms. If the particle responsible for the weak interactions didn't have a very large mass, the weak interactions would not be weak. Radioactivity would be a relatively strong interaction. So where does the mass come from? So you might think, well, Newton told us that weight is proportional to mass, and Einstein told us that E is equal to mc squared, energy is related to mass. So that's great, but these guys didn't explain where the mass comes from in the first place. And that's where this guy, Peter Higgs, comes in. His theory is there on the blackboard behind him. And if I stand up just for a moment, you can see it's also embroidered on my pullover. Now, according to Mr. Higgs's theory, in addition to the particles on the previous slide, there should be another particle that he proposed called the Higgs boson. He proposed it in 1964, and it became, in some sense, the particle physicist's holy grail until eventually it was discovered in 2012, as I'll be discussing in a moment. So, of course, the idea is relatively technical, but let me try to give you some sort of flavor by analogy of what Higgs and others proposed. So they said, think about a particle going through empty space. Well, actually, space is not empty. You should think of it as being an environment which has a field of stuff in it. Now, we've heard about electromagnetic fields. We've heard about gravitational fields. Let's imagine a different type of field, a field which is homogeneous and isotropic, spread throughout the universe. So I like to compare it to a field of snow in Siberia in the middle of winter. Snow as far as you can see. So supposing you're a particle going through the universe. The analogy would be somebody trying to cross Siberia. So if you're wearing skis, you skim across the top of the snow, you go very fast, and that's like a particle without mass that does not interact with this Higgs snow field. Like, for example, the photon, a particle of light which always travels at the speed of light. On the other hand, supposing that you don't have skis, you have snowshoes. Then, of course, you sink into the snow, you go slower, because you interact with this medium, the Higgs snow field, and that's like a particle with mass, like the electron, which interacts with the Higgs and travels at less than the speed of light. And then finally, maybe you've only got boots. When you have boots and you're going to sink very deeply into the snow, you're going to go very slowly. That's like a particle with a large mass that travels much less than the speed of light because it interacts strongly with the Higgs snow field. Okay, so that's all fine. But then what is snow made of? What's the quantum of snow? Of course, it's the snowflake. And analogously, you can consider the Higgs boson as being the quantum of this Higgs field, the snowflake of particle physics, if you like. So as already mentioned in the very kind introduction, I got interested in the Higgs boson in 1975, and together with two colleagues, we studied how it might look like in experiments. Now, in those days, long time ago, these ideas were regarded as being very speculative. And so that was one of the reasons why we didn't want to encourage big experimental searches for the Higgs boson, but we did describe to experimentalists how it might look so that they wouldn't miss it if indeed it was produced in their experiments. In fact, of course, many years later, engineers at CERN built the Large Hadron Collider to answer Gauguin's questions, and in particular, to look for the Higgs boson. So large, it's got a circumference of 27 kilometers. Actually, it's buried in a tunnel about 100 meters underground, so you don't see anything very much from the air. If you go inside the tunnel, this is what you see. You see a string of magnets curving away into the distance. And as I mentioned, these experiments set out to answer Gauguin's big questions. So one of them is the origin of mass. That's where the Higgs comes in. Maybe they can also reveal the nature of dark matter, as I'll be describing later on. They study the primordial plasma that filled the universe when it was very young, and they're studying the small differences that exist between matter and antimatter that might explain how the matter in the universe originated. So when it's in operation, there's thousands of billions of protons circulating in both directions through the ring. Each of them has approximately the energy of the fly, and they make maybe a billion collisions a second. And we look inside those collisions for fundamental particle physics. So how do we do that? Well, around the ring, there are 4 collision points, and at each collision point, there is a big experiment. So 2 of them, called ATLAS and CMS, co-discovered the Higgs boson and are now looking for dark matter. Another one, called ALICE, is studying the details of this primordial cosmic plasma. And then there's another one called LHCb, which is dedicated to studying the small differences that exist between matter and antimatter. And I'm happy to say that Indian physicists are participating in 2 of these experiments, namely CMS and ALICE. Now, I should say that although these experiments are done at CERN, they're done by literally thousands of physicists from around the world. So here is a map, and these different colors represent the home countries of scientists working at CERN. There are now something like 100 different countries represented. So there's the member states of CERN in Europe. There's associate member states in blue, light blue, including India, and there are other countries around the world with which we collaborate, including Russia and the United States. And as you can see, there's a very large contingent of physicists from India working at CERN. So in 2012, these physicists discovered the Higgs boson, and this created tremendous excitement in the world of particle physics, what I like to call mass Higgsteria. So this was created when the ATLAS and CMS experiment started seeing events which could be due to the production of a Higgs boson. Now, the Higgs boson is kind of difficult to see. It's a very short-lived particle, so you don't see the particle itself, but if you're lucky, you may see what it decays into. So one possibility is that it decays into 4 muons, and this is a candidate observed by the ATLAS experiment for such a decay of the Higgs boson. So you see 1, 2, where are they? There's 2 more red lines, which are possibly muons produced in the decay of a Higgs boson. So in this picture here, this cross-section picture here, you can see there's many other tracks coming out marked as yellow, and you can also see little blobs here, which are deposits of neutral energy, maybe photons. So CMS also observed interesting events, and here's one example of what they saw. Again, you see these yellow tracks of charged particles. You see deposits of energy without tracks, neutral particles. And you see these big red towers here. Those are 2 deposits of large amounts of energy by neutral particles. There's no track pointing towards those red towers. And those neutral particles were probably photons, and they could have come from the decay of the Higgs boson, a decay that we calculated back in 1975. So on July the 4th, 2012, the ATLAS and CMS experiments gave a seminar to announce their results. And being July the 4th, we call it Higgs Dependence Day. And I like this picture for a couple of reasons. Here you see Peter Higgs, whom I've already mentioned, for proposing the Higgs boson. And here is Francois Englert, who proposed a similar theory. And these 2 shared the Nobel Prize in 2013 for the discovery of the Higgs boson. And down here, outlined in red, is Fabiola Gianotti, who presented the results of the ATLAS experiment that day and is now the Director General of CERN. So that goes to prove that in physics at CERN, we have no glass ceiling. Okay, now what happened on July the 4th was that the 2 experiments announced they discovered a new particle. But was this really the Higgs boson or not? So we had to do some work to try to see whether this was really the missing piece in the particle jigsaw puzzle. Did it have the right shape? Did it have the right size to be the missing link in the standard model? And this was something that I worked on with my then student, Tirong Yu, back in those days. And well, here I just show you the current set of observations which convince us that this particle that we're seeing really is a Higgs boson. So this particle is supposed to give particles, the other particles, their masses. And to do that, it has to interact with other particles proportional to their mass. And this plot checks that that's actually consistent with the data. So here are particles that range over a factor of 1,000 in mass, but their couplings to the Higgs boson are in very good agreement with Peter Higgs's theory. So that was a motivation why in 2013 the Swedish Academy gave the Nobel Prize for Physics to Peter Higgs, whom you see here, and Francois Englert. And in their citation, they said, "Today we believe that this particle is beyond any reasonable doubt a Higgs boson." And my student and I were very proud because that quotation was actually taken from our paper. Although what the Nobel Prize Committee didn't know is that although we wrote that in our paper, when we sent the paper to be published by a journal, the journal said, beyond any reasonable doubt is not a scientific judgment. So we had to take that phrase out of the published paper. So it wasn't good enough for the journal, but it was good enough for the Nobel Prize Committee. So the discovery of the Higgs boson was a big deal. As I already mentioned, if it didn't exist, there wouldn't be any atoms because massless electrons would escape from nuclei at the speed of light. In fact, there wouldn't be any heavy nuclei. And weak interactions would not be weak. Life would be impossible. Everything would be radioactive. So the discovery of the Higgs boson was a big deal. What next? So I'm going to paraphrase the title of this James Bond movie. Of course, I make a few changes in the cast. So here we see Peter Higgs, here we see Fabiola Gianotti, and I changed the title of the movie from The World Is Not Enough to The Standard Model Is Not Enough. Why do I say that? Because if we calculate the properties of empty space in the Standard Model, it looks like it's unstable, that eventually empty space will collapse. The Standard Model doesn't explain the dark matter in the universe. The Standard Model doesn't explain the origin of matter in the universe. So, there's a couple of Gauguin's big questions here, which have not yet been answered, but they may be answered by the LHC, as I'll be discussing later on. Now, there are other important questions also, which can be addressed by the LHC, but I'm going to be focusing in the rest of this talk on these three here. So, as I mentioned earlier, we are in a not empty space exactly. We're in an environment where there is a Higgs field, and that Higgs field, the depth of the snow, if you like, is not zero, but it's not very big either. And the depth of the snow, the depth of the Higgs field is represented by this red dot. But theoretically, there's another possible configuration over there on the right-hand side where the Higgs field is much denser, the snow is much deeper, if you like. And we certainly don't want to live there, because if we lived over there, then the universe would collapse in a sort of big crunch under the pressure. Now, the problem is that, like everything else, the Higgs field is subject to quantum fluctuations. So you have to imagine the Higgs field is vibrating, and these quantum fluctuations could cause it to tunnel through into this big crunch state. And as I mentioned, that would be a catastrophe. Not just that, but there's the issue of whether the universe should have collapsed already. This is because early in the history of the universe, we expect the fluctuations in the Higgs field value to be much larger, and basically you could just jump straight over the barrier and into this big crunch configuration. So how could we prevent that, theoretically? So one possibility is to erect an infinitely tall barrier, which would prevent these quantum fluctuations forever taking us into this big crunch. And one example of a theory that provides such an infinite barrier is the theory of supersymmetry, which was already mentioned in the introduction, and which I'll return to later on. Okay. The next thing that I want to discuss is dark matter. So dark matter was proposed by the Swiss astronomer Fritz Zwicky in the 1930s. So what he was doing was he was observing galaxies in a cluster called Coma. And he found that these galaxies were moving around each other too quickly in the sense that to hold the galaxies together, to prevent them from flying apart, you would need a stronger gravitational field than is provided by the visible matter. So he said, aha, there must be additional invisible dark matter. So that was in the 1930s. But people were not convinced for, I would say, for decades. And an important role in convincing people that this dark matter hypothesis was actually correct was played by the astronomer Vera Rubin, whom you see here. So what she did was that she observed stars and gas orbiting galaxies. So Fritz Zwicky observed the motion of galaxies in clusters. Vera Rubin observed the motions of stars inside galaxies. And her observations also required a stronger gravitational field than provided by the visible matter. So this was strong further evidence for dark matter, and subsequently there have been many other convergent pieces of evidence for the existence of dark matter. So this is an illustration of the sort of measurement that Vera Rubin made. This is a more recent measurement. So here you see a rotation curve. So this is the orbital velocity of stuff going around a galaxy. And you see that the velocities are pretty much constant out to very large distances which are much larger than the visible mass in the galaxy. Now, if you just calculated the gravitational field associated with the visible mass, then it would go down. And because the gravitational field goes down, also the velocities of orbiting stars would also go down. But the velocities don't go down. So that tells us that in addition to the ordinary matter in a galaxy, there must be this additional dark matter in a sort of halo around the galaxy. So Vera Rubin's work in the 1970s and subsequent work in the 1980s, I think, convinced pretty much everybody that dark matter was something real. So what could it be? So one possibility, the favored possibility, is that it's made of some type of unknown particle. Now, there's various different ideas for what these unknown particles might be. And one of them is this theory of supersymmetry that I've mentioned previously. So according to this theory, every known particle represented by these small balls has a supersymmetric partner particle, which is heavier. So I represent it with this bigger ball. And these supersymmetric particles have the same electric charges and other interactions as the regular particles, but they have different spins. All elementary particles spin around like tops, but the supersymmetric particles spin at a different rate from regular particles. Now, according to the theory, these supersymmetric particles could be produced at the LHC, and that has been and continues to be one of the main subjects of research at the LHC. In fact, just this past week, we had a meeting in India to discuss the prospects for future studies of supersymmetry at the LHC. Okay, so here in a little bit more detail, I show on the left the standard model particles, and on the right, I show the corresponding supersymmetric or SUSY particles. So they have the same colors, some little symbols on top. So the same colors, they have the same interactions. The tildes, they have different spins. And among these, circled in black here, are particles that could provide the dark matter. So these are neutral, massive, supersymmetric particles. So how do you look for such particles? Well, if you produce them at the LHC, you wouldn't see them directly because they don't have electric charges, they have only weak interactions. So how do you know they're there? Well, they're going to carry away energy and momentum. And this is a computer simulation of what you might see. So you're looking down the collision axis, and in this simulation, you get a bunch of visible particles coming out on one side and nothing visible on the other side. And that's because in this simulation, that's where the dark matter particles went. So this is something that could happen in supersymmetry. It could also happen in other theories. But this is the key signature that the Large Hadron Collider experiments are looking for. So far, they haven't seen anything, but this meeting that we had in India over the past week has been discussing new ways of looking for supersymmetry, which will be continuing in the coming years. Now, another way that you might look for particles of dark matter is, according to astrophysicists, there's dark matter everywhere. There's dark matter here in my room, there's dark matter in your room, okay? So there must be some way of detecting it. Well, it's very difficult on the surface of the Earth because you've got cosmic rays, you've got radioactivity. But if you go deep underground and if you shut out cosmic rays, then maybe occasionally you could see an event where an incoming particle of dark matter hits a nucleus or an electron inside a big detector and deposits some energy, which you can then detect. So there's experiments around the world that are looking for such effects, although they also haven't seen anything yet. Okay, so that was the dark matter. How about the origin of the matter itself in the universe? Well, here we come back to matter versus antimatter. So antimatter interests a lot of people. I'm not sure whether it's because of Star Trek or whether it's because of Dan Brown's books and movie. Anyway, we physicists can't make enough antimatter to power up the Starship Enterprise or to blow up the Vatican. But that's not what we're interested in doing. What we're interested in doing is trying to understand the very small difference that exists between matter and antimatter. So antimatter was postulated by Dirac in the 1920s. He said that every known particle should be accompanied by a particle with opposite internal properties like electric charge, but the same mass. It's not the same thing as supersymmetry. Supersymmetry is same charge, different mass. Antiparticles are opposite charge, same mass. And so these particles were discovered in the cosmic rays. And since then, we've been studying them in accelerators. And in fact, they're used in medical diagnosis and things called positron emission tomography scanners. Now, Dirac, and I think everybody else, for many years, thought that matter and antimatter would be exactly equal and opposite. Turns out that's not the case. Back in the 1960s, it was discovered that their interactions are slightly different. And the Russian physicist Sakharov proposed that that could explain why the universe today has lumps of matter, like you and me, but no lumps of antimatter that we can find. And there's an experiment at the LHC which is dedicated to trying to understand this matter-antimatter difference. So what was the idea of Sakharov? Here he is, by the way, visiting CERN in 1990. So he said, well, we need a difference between the properties of matter and antimatter, and that we've seen in the laboratory. We need interactions which are capable of creating matter. Those are expected in theories, although none has yet been observed. And we need some sort of direction of time, which is provided by the expansion of the universe. You put these three things together, and the universe could evolve into a state where there are more matter particles than antimatter particles. All the antimatter particles annihilate with some of the matter particles, and some matter particles are left over to make you and me. So that's the theory, and we're trying to figure out a way of how this can be made to work. So the final thing that I would like to mention is Einstein's dream. So Einstein's dream was to unify the fundamental interactions. For many decades, he tried to do this, but he never succeeded. Now, one of the ideas that he worked on was the possibility that there might be extra dimensions of space. And in some of those theories with extra dimensions of space, gravity would become strong at the high energies of the LHC. And in some of those theories, so this is speculation upon speculation upon speculation, you might be able to make microscopic black holes. Now, that would be very exciting because that would give us an opportunity to study quantum gravity in the laboratory. Now, some people got scared. They said, oh, if you make a black hole, isn't it going to eat up the entire Earth? But no, because it's a very small black hole and it vanishes instantly. And if you want to be convinced that these black holes are not dangerous, just remember all those cosmic rays bombarding the Earth, which would produce many black holes in the past. And if black holes were dangerous, we wouldn't be here. So black holes are nothing to worry about. Okay, that brings me to the end of my talk. So I hope I've convinced you that Large Hadron Collider at CERN, other particle accelerators, the world's most powerful microscope. And they're also, in some sense, telescopes. And as telescopes, they also address Gauguin's big questions. So what are we? What's the structure of matter? Where do we come from? What happened at the beginning of the universe? Where are we going? What's going to happen in the future of the universe? Experiments with particle accelerators may provide the answers. Thank you.
Thank you so much, sir, for such an interesting talk. And I'd always heard the phrase that more is unknown than the known. And indeed, everything that we can see in the universe is like the tip of the cosmic iceberg. And we are indebted to scientists and researchers like you who are trying to help us understand the remaining of the universe. Also, sir, I was very surprised to know that we have a very common perception that CERN is working a lot more than just particle physics, including cosmology. Like experiments performed at LHC helps us answering some of the biggest questions which are still unanswered in the universe. Thank you once again, sir, for this amazing talk. And now I would request you to take some of the questions which we have coming up in the comments and the chat. So
Okay.
our very first question, yes, our very first question, sir, is from Aman Jha. Why didn't matter and antimatter completely annihilate each other soon after the Big Bang? Why did matter dominate over antimatter?
Okay. So if you think back to the very early history of the universe, there will be particles and antiparticles running around. They will be colliding, and matter and antimatter particles could annihilate with each other. Now, the idea is that thanks to the Sakharov mechanism, the interactions of particles built up an asymmetry between the amounts of matter and antimatter. So a bit more matter than antimatter. Then those particles of antimatter, as the universe expanded, would have annihilated with some of the matter particles. But there would be some matter particles left over, and that's what we are made of. So I like to compare it to a dance where there are more of one gender than of the other, right? So two genders match up, but if there's more of one gender than the other, then that gender finishes up with what we call in English wallflowers. So if you like, we are made of matter, which is the wallflowers of the cosmic dance.
Thank you so much, sir.
Thank you so much, sir. The next question is from Vipul. He says, what if dark matter and dark energy are the concepts similar to ether? We believe they exist, but one day we might say that there is no dark matter or dark energy. It's like we are trying everything possible to prove they exist. But what if in the end we realize there is no dark matter or dark energy, just like in the case of ether about 100 years ago?
Okay, well, I think there's a difference with the ether. So nobody ever produced any experimental evidence for the existence of the ether. And I remind you of the Michelson-Morley experiment. They set out to measure the Earth's motion relative to the ether, and they found nothing. So they found no experimental evidence for the ether. In the case of dark matter, we have all these rotation curves. We've also got observations of the cosmic microwave background that I didn't have time to discuss, which convince us that this dark matter is a real thing and that it acts gravitationally in the same way as regular matter, it's just that we can't see it. Now, dark energy is a little bit more subtle. There's not so much, if you like, observational evidence, except if we look at the overall expansion of the universe. So if you remember the picture that I showed back towards the beginning of the universe gradually expanding. Now, if you look carefully, the expansion was slowing for a while, and then it started speeding up. And so the shape of the expansion of the universe is a little bit like a trumpet. Okay, so it's got a sort of tube, and it gets bigger. Right? And that acceleration in the expansion of the universe requires something that has, in some sense, negative gravity. So rather than attracting, it's repulsive. So that's not matter. That has to be something completely different. And we think it's just a density of energy in empty space. Now, we have various ideas for how we could detect more directly dark matter. Detecting directly dark energy is more difficult. So if you have a good idea for that, no, maybe there's a Nobel Prize there somewhere.
Thank you, sir.
Thank you so much, sir.
Yes, sir. So we have our next question from Nidhi. And the question is, why do particles interact differently with the Higgs field? There are some particles that do not interact with, while others interact with the field to a great extent. What is the deciding factor?
Okay, well, in some cases, there are basic fundamental symmetry reasons that explain why it is that a particle like the photon, for example, does not interact with the Higgs field. So that's not so much of a problem. What I would regard as being more of a problem is to explain why the particles that do interact with the Higgs field have such different interaction strengths. So, for example, consider the electron and the muon. So, according to the standard model, the electron interacts 1/200 times as strongly as a muon. But how did that come about? Why is it that there's this factor of 200? Why is it that, for example, the top quark weighs, in fact, 1,000 times more than the muon? We don't know. So at the moment, this is something which we have discovered in nature, and we can describe it in the Higgs theory, but we don't have a fundamental understanding of where these differences in particle masses come from.
Thank you so much, sir. The next question is from my side. So I always wanted to ask this question. Mesons, such as positive or negative pions, exist because they have a quark and an anti-quark pair of different flavors. For example, a positive pion is made up of an up and anti-down quark. Both belong to different flavors, so they don't annihilate each other. But what about the charmonium system composed of quark and an charm quark and an anti-charm quark? Why don't the two particles annihilate each other?
Well, actually they do. It's just that they do it slowly. And we think that's because the strong interactions that we talk about, the strong interactions that hold nuclei together, they're very strong if you are at large distances. So if you're 10 to the minus 12, 10 to the minus 13 centimeters apart, they're very strong interactions. Which as you go to very short distances, the strong interaction gets weaker and weaker. And this is a property known as asymptotic freedom, which was discovered in the 1970s. And it's been verified experimentally. And the people who discovered this property got the Nobel Prize in the early 2000s. So in the case of charmonium, the charm and the anti-charm quark could annihilate. They do annihilate, but they do it slowly because of this asymptotic freedom property.
Okay, thank you, sir.
Thank you, sir. The next question is from Effie. Is there a connection between dark matter and black holes?
Well, of course, with the recent discovery of gravitational waves from mergers of black holes, a lot of people have been saying, well, couldn't the dark matter be made of black holes?
Correct.
And the answer is probably not. At least not the sorts of black holes that have been observed emerging by the LIGO and Virgo collaborations. So those weigh several dozen times the mass of the sun, each of them. And there's all sorts of limits coming from astrophysics and cosmology on the abundance of such heavy black holes. But there is a little window for very small black holes, not particle small, but astrophysically small. And so it's possible that such black holes could make up the dark matter, although nobody really has a very good theory of why that should be the case. But that is an open possibility.
Thank you, sir. The next question is from Wendy, and she asks, how is pair production different from the Bright-Wheeler process?
How is pair production different from the Bright-Wheeler process?
In both the processes, we have matter energy, pure energy is converting into matter. But in what is the difference between the two? Is there any difference in the mechanism of the two processes?
Well, I must confess to ignorance as to what the Bright-Wheeler process is. I mean, it's always possible to convert energy into pairs of particles with opposite internal properties, like electron and positron, or muon and anti-muon. So I suspect the Bright-Wheeler process must be some particular example of that. I'd have to Google it to find out.
Okay, so no problem.
Thank you, sir. Sir, the next question is coming from Majid Nasir. What is the origin of mass in the universe? Dark matter or something else?
So the origin of mass, as I said, has to do with the fact that you've got this density of Higgs throughout the universe. And it has nothing directly to do with the existence of dark matter. Now, that said, the Higgs idea for the origin of mass is something that works extremely well. But we come back to the same problem of understanding why the scale of masses is what it is. And if you do a theoretical calculation, there's a danger that you're going to find that the masses should be much larger than what they actually are. And so one of the ideas that tries to prevent that from happening is called supersymmetry. And there are other theories as well. Now, as I already mentioned, supersymmetry contains a candidate for dark matter. And some of these other theories also contain candidates for dark matter. So it's possible that the dark matter is due to some extra, as yet unknown interaction or particles that help stabilize the overall scale of particle masses and the Higgs boson. But that remains to be established.
Thank you so much, sir. The next question is from Ritesh. How is distribution of dark matter different from that of antimatter in the universe?
Okay, so as far as we can tell, there are no large concentrations of antimatter in the universe. Of course, sometimes you pair produce electrons and positrons if you've got a very strong electromagnetic field, for example, around a pulsar or something like that. But there's no big lumps of antimatter. And there's limits coming from astrophysics and cosmology that basically tell us that there can't be any big lumps of antimatter anywhere in the visible universe. So there's no, if you like, there's no distribution of antimatter to discuss. Now dark matter, we think, does not have exactly the same distribution as regular matter, and that's because of the difference in its interactions. And as I mentioned, if you look at a typical galaxy, you've got visible matter in the middle, and then you've got this sort of dark matter halo outside. And the fact that the halo extends outside is because the interactions of dark matter are weaker, and so they don't dissipate energy as effectively as regular matter, and so they don't clump together.
Okay.
By
Thank you,
the
sir,
way,
for that. The next,
in the meantime, I discovered what the Bright-Wheeler process is.
Okay.
The Bright-Wheeler process is when you collide two photons and you make a pair of particle and antiparticle. So it's just one example of how if you some concentration of energy, in this case provided by two photons, can be converted into a particle-antiparticle pair. So it's one example.
okay. Thank you, sir. So the next question is coming from Shashank, and he says that there is a theory that dark matter is composed of axions. Axions are yet to be discovered. Do you think that dark matter is made of such particles? What are the other possibilities?
So yeah, I focused on the idea that dark matter might be made of relatively massive individual particles. Axions, they're particles that we call bosons that like to clump together in a coherent way. So axions could provide the dark matter by existing in the universe in coherent waves. So this is certainly an open possibility. And in fact, I'm involved in an experiment which is trying to look for such coherent waves of clustered dark matter bosons. I would regard that as being, an idea for the possible nature of dark matter, which is sort of on a par with the massive dark matter particles that I discussed in my talk.
Okay, sir. Thank you very much. And the next question is by Karen. How long before we have an experimental evidence of string theory?
I have no idea. Back in the 1980s, when people started thinking that string theory might be a theory of everything, people were quite optimistic that they might be able to find some evidence in the relatively near future. But I think since then, people have got a little bit discouraged. So I think there's a couple of ways in which you might look for evidence of string theory. So one is to see some characteristic prediction for the known particles or their interactions, which is a prediction of string theory, but was not predicted otherwise. And so far, nobody has succeeded in coming up with a sort of a smoking gun of that type. Another thing which you can look for is some effect which is just not predicted in the standard model at all. And this is something that I've worked on in the past. So one possibility is we know there's a problem reconciling quantum mechanics and general relativity. So maybe one or the other is wrong at some level. Of course, they work very well, but there might be, under extreme conditions, either relativity or quantum mechanics might break down. And so we proposed various tests of quantum mechanics. And in fact, just a few days ago, there was a paper which found yet again that quantum mechanics works just fine. As for a violation of relativity, so one idea that we suggested was that maybe energetic particles would travel at a different speed from less energetic particles. And this is an idea that we supported with some sort of approximate calculations in string theory. And this is something which has generated quite a lot of interest. I think our original paper on the subject has now got over 1,000 citations. And in fact, just a couple of weeks ago, We produced an enormous review of how one might look for such effects, but they haven't been seen yet.
Thank you so much, sir. There are some more questions, but because of time constraint, we'll be ending this here. So, on behalf of the Secrets of the Universe and Gurukul Academy, I once again extend a very hearty gratitude to Professor John Ellis for accepting the invitation and sharing with us his valuable thoughts. Your thoughts have enlightened our minds and have shown us a new path. Here, I would also like to mention that these lectures are our endeavor to take global science to the students residing even in the remotest corners of the nation. We also thank our partner, including the Physics Club of Aizer Behrampur, 137 Inverse, for their support. Finally, I would like to thank all of you for joining us from different parts of the world. It is your love and support that keeps us going and inspires us to continue our work. Stay tuned to our channel for more such talks on coming Saturdays. Thank you.